last talk of the day. Thanks everybody for sticking around. We have kind of remarkably high numbers and low atrophy for an event like this on the second day, last talk. So means that I think we're still talking about highly relevant things. There will be, after this session, the day is over. You're welcome to disperse. And there's actually one final coffee break set up for us as a going away snack.
Thanks, Andy. So I'm not hiring. I hope at some point to get hired, but not yet. OK, so already a question? Oh. So, OK. So I have a little, I have much more slides, but feel free to interrupt at any point to ask some questions. So today I will present what I call Mobile Millennium on the Cloud, which is a joint research project between the AMP Lab and the Department of Intelligent Transportation System here at Berkeley. So as Michael Franklin said yesterday, our research is all about making big applications that combine crowdsourced data and complex statistical model that can then run on the cloud. And for that, we have been telling you about the wonderful software stack that we developed here at the AMP Lab. And you have tried it yesterday, but you still probably wonder how it works in a big research project. And this is why we'll talk today how we use Spark inside this research project on transportation that is called Mobile Millennium. And this was the first big benchmark of Spark on a real-world application. So I hope to convince you by the end of the talk that now is the time for Spark to run, to escape out of the lab and to run on your data. So I will briefly present the crowdsourced data we're using in the Mobile Millennium project. And I'll then explain how we use machine learning for traffic. So to motivate the algorithm, I will need a very small detour into machine learning, but it will be brief and it will have no math. So the algorithm, as you will see, begs for being parallelized. And Spark was exactly what we needed for this case. So I'll show the performance improvements we got by using Spark. And to conclude, I will share with you a few points that you should keep in mind when you want to use Spark on your own systems. So our application is traffic, car traffic. And if you came from the South Bay today, it will come at no surprise to you that congestion on the streets in California is still a major challenge. And estimating traffic still remains an open question, especially for urban streets, which is called the arterial road network. And so far, the most promising source of data has been the GPS of your cell phone. This is the data we want to leverage to infer traffic. So what does this data look like? So every day, we collect traces of GPS from a taxi cab in San Francisco. So here you can see the San Francisco app appearing with here the Bay Bridge. And that's about a couple of thousand vehicles for which we have access. And we get a couple of million points per day. And the road network covered here is about 50,000 road links. So using these GPS points, we want to solve an estimation problem. So the traffic condition, as you can imagine, will influence the behavior of the vehicles we observe. And by observing the variations in this behavior, we want to reconstruct the current traffic congestion. And the crowdsourced data is very noisy, and car traffic is a complicated phenomenon. So we combine a statistical approach with a physical model. So this is these GPS points by themselves are not very useful. So we first have to map them onto the road network. And we need first to reconstruct the trajectories. So here you see the actual inputs of our estimation engine, which are the reconstructed trajectories on the road network. So all this filtering is done inside Mobile Millennium. Mobile Millennium is a traffic information system which is designed to mix different sources of data to produce some traffic estimates in real time. And the whole stack is quite large. It's about 600 lines of Java code in total, running on 10 machines and five databases. So for today, I'll just focus on this small module here, which is the arterial estimation engine. And so the statistical algorithm that we use require a lot of computations. And we use the AmpLab stack to offload these computations to some clouds. So from the perspective of the whole system, the cloud stack, badass, is simply another dependency that's in the code to offload all the computations. So once we have mapped all these taxi data, how do we estimate traffic congestion from it? So at the input, we have a description of the road network, all the road links, and on each of these links, we assume that we want to know the travel time that it takes to cross over all these links. And this travel time is stochastic in nature. So each of these travel time will be represented by a probability distribution. And let's assume that this probability distribution is parameterized by the mean and the variance. So let's be a bit more concrete. And I'm going now to motivate 6 months of research in 5 slides and 2 minutes, but it will be worth it. So to take a concrete example, let's consider here this road network. So each of these links here have some travel time distribution. And we're going to observe some vehicles coming here. And so for example, it comes here. We see a GPS observation coming. And then at the end of the road, it sends another GPS observation. So we know the travel time on this link here, on this road link. So we get a bunch of them for different vehicles. And then we can combine them to compute a histogram and some means and some variance. So we get the estimate of the travel time on this road link. So of course, we do not observe exactly the vehicles at the intersections because we do not control this, but this is the spirit. Well, life is unfortunately not that simple because this is not what we really get. Because remember that we observe this taxi every minute, and in the span of a minute, a vehicle can do a lot of travel. So for example, we would see, so our observation will typically be over several links. So what we know is how long it takes to go between here and here over the links A and B. But what we really want to know is how long it takes on link A and how long it takes on link B. We need to know the proportion on each of them. So can we at least estimate this missing information? So the inner statistician in you will say, yes, we can, because we can sample some estimates of it. So we can take this complete time and use a model and then compute some samples for each of the travel times for these links. And then we do it for all the observations we have. And we can run again the same procedure as before, compute some means and variance for each of the links. So it's nice. It seems to work. There is simply one catch, which is to do this split here, we need a model in the first place, but we are learning the model. So it's a kind of chicken and egg problem. But the computer scientist in you will say, well, since we're taking a model to learn another model, why don't we iterate? Start with a model and learn a new one, and then iterate again and again. So that would be a completely correct intuition. This procedure to learn the parameters has a name. It is called expectation maximization. And it is an iterative algorithm that works in 2 steps, the sampling step that we saw before, and the learning step, the M step, which corresponds to computing the histograms, the means, and the variances. So to give you some figures, the network for San Francisco, the road network is 50,000 road links. So we'll have 50,000 parameters to estimate. We'll consider, typically for a batch experiment, about 50 million observations. And each of these observations will span, on average, 4 road links. So that makes about 200 million partial travel times. So it's not such a big data set, but when we do this sampling procedure, we actually multiply the size of this data set by 1,000, or even more sometimes. So it gets quite large. And why is it interesting for Spark and for machine learning? Well, this procedure, expectation maximization, is a very general pattern, and it makes a lot of sense for machine learning research to optimize this kind of iterative pattern. So how does it work from, so now we are done with the machine learning part. How does it work from a systems perspective? So we have all the observations stored usually onto the database or the Hadoop file system. And we first spread them inside an RDD as a chunks on every of the worker node. At the same time, we initialize the master with some sets of parameters describing the word network and our current guess for the travel time distributions. Then, in order to perform the sampling, we are going to send a copy of these current parameters to all the worker nodes. From these, we'll generate all these travel time samples, so all these thousands of travel time samples for each observation. These travel time samples will be then aggregated for each road link on a different. So physically, it is the same set of machine. I split them to explain more easily. And then for each link, then we'll generate a new set of parameters, of learned parameters, which are then collected by the master. So far, this is the standard map, shuffle, reduce pattern that is in MapReduce and Hadoop. The big difference is how we can use Spark to keep all these observations in memory, and how we can then use it to more efficiently iterate over this pattern again and again. So how does it translate into the code? This is the actual code. That's it. This is the whole code. So from a machine learning perspective, it's very convenient. Spark is very convenient. We start by loading these observations. As usual, we load them here from Hadoop file system. We parse them, we cache them, and then while waiting for convergence, we take each of these observations, we sample them in the step by generating some samples, and then these samples are grouped together for each link, and for each link we learn a new set of parameters, and these parameters are then collected back by the master. This code is we actually wrote the same code without the red corresponding to Spark in our first experiment on a single node. And then when we wanted to add Spark, well, we just added the red here. That was it. So as you see, so the algorithm is quite small, and the challenge really lied into making it work at a large scale. So when we started to run it multi-threaded on a single big machine, and it would take too long to even be able to run real-time estimation. So for 1 hour of data, it would take more than 3 hours to just process it and get some estimates back from it. And so this is why you really see that a distributed version was necessary here. So does it make an impact to use an iterative framework? Because we could have used Hadoop or some question?
On the previous slide,
yes.
How are you sharing data between your iterations? Like, where does that state get threaded through?
So we first cache the observations here. Oh yeah, sure. So how do we share the data between each of the iterations? So all the observations are first cached here, and then from here for each observation is mapped onto samples. So so implicitly the RDD corresponding to the observations stays in memory, and we generate at every iteration a temporary RDD corresponding to the samples. This one is ephemeral, and then gets discarded once we learn the new parameters.
Oh, sorry, I didn't see fair perhaps. Okay.
Yes.
So where's convergence?
All right. So where does the convergence happens? Well, more precisely, we actually keep track of the previous parameters and the new parameter, and then we compute the difference. And once it starts to converge, then we stop here. Yes. Oh, so do you mean all these functions here?
Most likely parameter.
Oh, this one?
Yeah.
So, okay.
So I wonder if Scala has full-fledged math library for you to do all the machine learning calculation in log space.
All right, yeah. So the question is what kind of machine learning library we're using for this code. We rolled down our own machine learning library well, we reuse some matrix libraries from Java World, EGML. But then the rest of the code, how we represent statistical distributions, we wrote it by ourselves. So we have written, so I believe, Ariel will probably correct me, I believe there is a machine learning library written completely in Scala. We are not leveraging it directly, we're using our own code for this particular problem.
I mean, yeah, I mean, I think that's basically, I mean, I don't know of like a full-fledged machine learning library in Scala. I think there have been attempts to start building such a thing, but I mean, there's nothing, for example, that looks like R in Scala or something like that.
No, I'm not worried about the machine learning library. I'm worried about the math function.
Like linear algebra operations?
Okay.
Because the question was, I've been asked to repeat it, you know, low-level math operations such as linear algebra operations, vector, multiplies, matrix operations, things like that. Wait, so what were you guys using for that?
So for the for the math library behind it, we're using EGML. But so there are a number of options in the Java world. Nowadays, they are good enough that they come within 20%, 15% of the actual BLAS fast operation, like C operations.
Right, so the key is that in Scala you can use any Java library seamlessly, right? And Java has a pretty well-developed ecosystem around sort of basic math operations at this point.
Right, so we are nearly as efficient as using some C code directly. Okay, any more questions? All right, so so how good are we doing? So we tried a version of this algorithm that would reload the observation at every step, and it was pretty close to what would Hadoop do. So so it was about 3 times slower than using Spark in this case. So that had definitely an impact. And remember that most of the work here is done in the sampling, which is math heavy, and in the learning, which is also math heavy. So also, how well does this algorithm scale? So all the work can really be done nearly in parallel because each observation can be sampled independently, and each link can learn its travel time distribution independently. So it was really a good showcase for seeing how well it would parallelize. And so we ran this code on a research Hadoop clouds owned by the US Department of Energy. And we started first with 4 nodes with 4 cores each. And it was taking, so a 1 hour batch of data was taking longer than, well, it was taking nearly an hour and a half. And it would really scale nearly linearly. At the end, with the maximum number of nodes we could get, I think the whole code was running in 3 minutes for exactly the same configuration. We just switched one number, the number of nodes. So that was really convenient to try to iterate fast on the math behind it. So life is unfortunately not as beautiful as everything you would expect so far. And since we're keeping all the data in memory, you have to be careful in what you do. This is especially important if you use Scala, because Scala makes it very easy to use enormous amounts of memory without realizing it. And especially, so if your computations start to take a long time, we found a good strategy to actually sample a couple of nodes, look at the logs to see what the garbage collector would do. And when a task would run for a very long time, usually it meant that the garbage collector was running hard somewhere. So I'm not talking here about the problem with the caching strategy of Spark, but sometimes the computations we do inside can actually require them to have a lot of memory. And Spark is not necessarily aware of that. At least it was when we used it a year ago. And also, Scala, under the scenes, can use some inefficient collections. especially when you use complicated sequences of transformations, when you combine filters, group bys, partition, and so on. Here I'm talking about inside your loops, your programming loops. Because, for example, Scala may decide to convert an array into a list, and a list of doubles will be 2 to 3 times more, we will use 2 to 3 times more memory than the corresponding array of doubles. So this is something that you have to be aware of. Yes?
When you say Scala makes it easy to use massive amounts of memory on a node, how much data or memory is a lot?
Okay, so why does Scala can recur a lot of memory? Well, one example is when you use the filter pattern on an array. What Scala will do is actually create some option. So it will create a new object for every element in your array and create an array of these new objects. So if you had an array of integers, it will box everything to build this new array and then create a new array after that. So it may convert some efficient low-level primitive like arrays to arrays of objects and allocate new objects.
Yeah, but the question was how much data do you think is a lot? Like, I understand what you just said.
Yes.
And that helps. And also, what do you think is a lot of data?
Okay, so unfortunately, it really depends on your application. Oh yes. So the question was, yes, Scala can use a lot of memory, and how much is a lot, and how can we trace that? I don't think there is any good tools for that for now. Really, for now, I usually check the garbage collectors to see what is going on. This is definitely not a bulletproof answer. So if you're really having some memory issues, but this is a bit of a last resort, one hack is to actually keep the byte arrays of serialized data in the RDDs and then digitalize it on demand. Which we tried it. It added, I think, a 20% penalty in the runtime of the algorithm, but we could, but it cut, I think, by 30% the amount of memory required for our application. So it's really application dependent at this level. So this morning, you saw about this broadcasting mechanism. And in a machine learning task, it is quite common to share a large set of parameters between the jobs. And in our example, at the start of each job, we need the description of the word network. And also between each of the iterations, we need to share the updated parameters corresponding to the distribution of travel times on each of the road links. So when you look at this small code like this, okay, well, it's missing a bit, but it should be enough. For example, this is when we load the observations. We start from we need to provide a description of the word network for every observation to parse it. And when we use this code, Spark would ship again and again the network description, which is why and this is exactly the use case for the broadcast mechanism. So adding this broadcasting mechanism here, we could cut down the loading time of the data onto the cluster by nearly 80%, which was quite significant. Yes?
Was your network?
Okay, so.
Was your network stored in a serialized class format?
No, so the network was already, so what was the format of the network here? The network is a hash map containing a map from link IDs to link descriptions, plus also pointers between the links. Okay, so to conclude, I have shown here how we combined some traffic information research with with a cloud computing framework, which is quite advanced and very useful in this case. So using all the optimizations mentioned so far, we could achieve some linear scaling of our algorithm. And now as researchers, I really feel that we are not limited anymore by computations. we can now run our traffic estimation algorithms much faster than real time. And we can also run much more complicated model. So Dilip mentioned the simplicity of Hive, but one benefit we got with Scala is how we can combine it with all the frameworks, all the statistical frameworks that already exist, and all the, especially for using some linear algebra. And now, so we can combine all our research and all the deployment within a single language and within a single framework, which is very convenient for doing research. So thank you for your attention, and if there are still any questions, I'll be happy to answer them.
All right, thanks, Tim.